Hi, let's talk about electric flux. Electric flux is another quantity that we study or that we encounter when we study electrostatics. Electric flux is defined as the dot product of the electric field and the area vector. The direction of the area vector is the same as that of a vector perpendicular to the surface area. So we'll have an illustration on the next slide where we look into what a surface area vector or what an area vector is. Now, since electric flux is a dot product, electric flux is a scalar quantity, and its SI unit is Newton meter squared per coulomb from the units of electric field, which is Newton per coulomb, and a surface area, which is meter squared. And electric flux is represented by the Greek letter phi, which is a measure of the number of field lines passing through a surface. So again, electric flux is the dot product of electric field and the area vector. And conceptually, your electric flux is the amount of field lines that passes through a surface. So we have here illustrations of how an electric field can pass through a surface or the different orientations of the surfaces in relation or relative to the direction of the electric field. Generally, electric flux can be calculated with the formula electric field times the area vector cosine the angle between them, since it's the dot product. Now, we have here three kinds of orientations with respect to your surface area and the electric field. So we have here the first illustration where the surface area is directly perpendicular to your electric field. But however, when we factor in the angle between your electric flux and your surface area, we take the area vector. And what's the area vector? The area vector is the one that is perpendicular to the surface area. So as you can see here, we have the area vector that is perpendicular to your surface area. Now, when you look into our formula, EA cosine of theta, this angle refers to the angle between your electric field and the area vector. Now, for this case, we have your area vector, which is parallel and in the same direction to your electric field. And when your area vector and electric field are parallel with each other, then the angle between your area vector and electric field is 0, and cosine 0 is equal to 1. That's why for this case, you can actually have a formula where you can solve for electric flux with just multiplying electric field and your area vector. Now for this case, we have a slanted or diagonal surface where the electric field passes through. So in this case, we really need to factor in the angle, or we need to factor the angle between your electric field and your area vector, because your cosine theta will not be equal to 1. So to solve for the electric flux in case 2, then that is really going to be equal to EA cosine theta. Now for the last illustration, for situation 3, we have the surface which is parallel to the electric field. And when the surface is parallel to the electric field, the area vector will be perpendicular to the electric field. As you can see here, your area vector forms a 90-degree angle with respect to the electric field that passes. And when the angle is 90 degrees, remember that cosine 90 is equal to 0. And anything multiplied by 0 is 0. That's why the electric flux at this point will be equal to 0. Also, we need to remember the signs because there are positive and negative electric flux. Now, what do we mean by this positive flux and negative flux? The electric fields that are going in the surface are considered to be negative, and the flux that are moving outward or going out of the surface is considered as positive. Example, a flat rectangular surface with length of 2 meters and a width of 0.75 meters is rotated through a uniform horizontal electric field of 5 newtons per coulomb. What is the electric flux if the surface is a parallel and be perpendicular to the electric field? So we have two questions to answer. What will be the electric flux if the surface is parallel? So take note of that. It's the surface, not the surface vector. So if the surface is parallel and if the surface is perpendicular to the electric field. Now, for A, if the surface is parallel, then we can take that. If the surface is parallel, then we can take it as this one, where the surface is parallel to your electric field. And if the surface is parallel to your electric field, then therefore the area vector will be equal to 90 degrees. So therefore for letter A, we have the length of the rectangle, which is 2 meters, the width, which is 0.75 meters, and then we have the electric flux, which is 5 newtons per coulomb, and the angle is 90 degrees. To solve for it, your electric flux will be equal to EA cosine theta. But without going through the trouble of this one, if we look at our illustration, if this is letter A, then we can conclude that your electric flux is equal to 0. So any surface that is parallel to your electric flux will have any surface that is parallel to your electric field will have an electric flux equal to 0. Now for B, if the surface is parallel to the electric field, so you have the same given values, only that the angle is equal to 0 degrees, and cosine 0 is equal to 1. Therefore, to solve for electric flux, it's just E times A. And your electric field is 5 newtons per coulomb multiplied by the area. Now, what's the area here? Area is equal to the area of a rectangle is equal to length times width. So we put 2 meters times 0.75 meters. Now, what will be the result, or what will be your electric field? So that's 5 newtons per coulomb times 2 times 0.75. Your electric flux is 7.5 Newton meter squared per coulomb. So that's it. Simple as that. That's electric flux. Thank you very much for listening.